The fact that the moon rotates around Earth at the same rate as it spins around its own axis, so that it always keeps the same side facing Earth, might seem like an unlikely coincidence. But it's actually far more than just coincidence. In fact, this kind of synchronization is entirely normal in the solar system and likely throughout the universe. For example, most moons of Mars, Jupiter, Saturn, and Neptune are rotationally synchronized with their planets. Even Mercury, the planet closest to the Sun, is partially synchronized in its rotation with the Sun. A day on Mercury lasts 2/3 of a Mercury year. This synchronization occurs due to gravity, more precisely due to so-called tidal forces. According to the classical formula of Newton's law of universal gravitation, the gravitational force is proportional to the product of the masses of the attracting bodies, and inversely proportional to the square of the distance between them. However, celestial bodies have finite size, so some parts of a body are closer to the other object than others. Consequently, the closer parts experience a stronger gravitational pull than the more distant ones. This results in deformation. The body becomes slightly stretched toward the attracting object. This effect is stronger the more intense the gravitational field in the system. That is, the greater the mass and density of the gravitating body. The densest cosmic objects, such as black holes, produce truly monstrous tidal forces. For instance, if you were falling into a black hole feet first, tidal forces would begin stretching your body from your feet to your head. Physicists, with a touch of dark humor, call this process spaghettification, and it would ultimately tear you apart. Yet even less exotic objects, stars, and planets are capable of generating tidal forces powerful enough to destroy bodies that venture too close. This critical distance is known as the Roche limit. For example, in 1992, Jupiter's tidal forces tore apart comet Shoemaker-Levy. It's believed that tidal forces destroyed celestial bodies whose fragments later formed the rings of Saturn, Jupiter, and Uranus. Or, more likely, these forces simply prevented any massive object from ever forming at the distances from the planets where the rings now reside. Our moon, however, faces no such danger. It orbits Earth at a distance roughly 20 times greater than the Roche limit. For an object like the moon, this limit is about 11,200 to 11,800 miles. But that doesn't mean tidal forces have no effect on it at all. Under their influence, the moon is slightly deformed into an ellipsoid stretched toward Earth. Ideally, the bulge of this ellipsoid should lie along the line connecting the centers of mass of Earth and the moon. However, the moon both orbits Earth and rotates around its own axis. If a body rotates around its axis faster than it moves along its orbit, the tidal bulge leads the center line. If it rotates slower, the bulge lags behind. Because of this offset, a horizontal component of gravitational force arises, acting against the direction of rotation. Thus, if a body rotates faster than it orbits, gravity slows down its rotation. If it rotates slower, it speeds it up. It is precisely this mechanism that allows tidal forces to synchronize a moon's rotation with its orbital motion. Over time, the system reaches equilibrium. This is likely exactly what happened to the moon in the distant past. Its original rotation period differed from its orbital period, but gradually tidal forces adjusted it until it became locked, always showing the same face to Earth. By the way, Newton's third law hasn't been repealed. If tidal forces act on a moon, they also act on the planet itself. Earth is no exception. The moon's gravity deforms our planet, primarily the surface of the oceans, causing the tides. Moreover, Earth rotates around its axis faster than the moon orbits it. Therefore, according to the mechanism described above, tidal forces are slowing down Earth's rotation, lengthening our day by approximately 2 milliseconds per century. At the same time, due to the conservation of angular momentum, the moon gains orbital speed and its orbit expands. In other words, the moon is slowly drifting away from Earth at a rate of about 1.5 inches per year. Essentially, the same synchronization process that is already completed for the moon is now unfolding in reverse for Earth. Earth is slowing down while the moon moves farther away. Someday, billions of years from now, the Earth-Moon system will become fully synchronized. Earth will always face the Moon with the same side, just as the Moon does with Earth today. At that moment, the Moon's orbit will stabilize and its retreat will cease. Subscribe to the channel. There's even more fascinating stuff ahead.